Well, I think the trouble with string theory is that there isn't any connection with observations. As far as I'm probably taking too strong a view here, but the mathematics, I mean, it's largely driven by the mathematics as far as I know, which is in itself is not an objection as far as I'm concerned. A lot of what I do is driven by the mathematics. But the trouble with string theory is it's supposed to be a theory of the way the world operates. And if the number of dimensions of space is just wrong, I can't take it seriously.
In physics, where the mysteries of the universe are uncovered and our understanding is perpetually tested, Sir Roger Penrose holds a prominent position. Renowned for his advancements in cosmology, black hole theory, and mathematical physics, he stands out in the scientific community for his unconventional views on dark matter and the widely acknowledged string theory. Join us as we explore Sir Roger Penrose's intriguing propositions, challenging the validity of string theory and suggesting that dark matter may not be precisely as it seems. String theory stands as one of the most debated concepts in modern theoretical physics. It endeavors to reconcile two pivotal 20th century physics theories, quantum mechanics and general relativity. According to this theory, rather than particles being point-like, they consist of minuscule vibrating strings, which play a fundamental role in shaping our universe. The crux of string theory emerges from the acknowledgement that while quantum mechanics elucidates particle behavior at atomic and subatomic levels, and general relativity deals with gravity on cosmic scales, the amalgamation of these theories results in deep paradoxes and mathematical inconsistencies. String theory seeks to reconcile these conflicting theories, offering a unified comprehension of the cosmos. String theory traces its origins back to the late 1960s, stemming from the groundbreaking contributions of scientists such as Leonard Susskind and Holger Beck-Nielsen. Its prominence grew with the formulation of the Veneziano amplitude by Leonard Susskind and Gabriele Veneziano, laying the groundwork for string theory and culminating in the inception of the first string theory model known as bosonic string theory. One striking aspect of string theory is its introduction of a novel scale concept. Unlike traditional quantum field theory, which depicts particles as dimensionless points, string theory proposes that they are infinitesimally small vibrating strings. These strings can oscillate at different frequencies and modes, akin to musical strings producing diverse tones. Each mode of vibration corresponds to a distinct particle. This framework elegantly addresses issues concerning particle mass. While the standard model relies on the Higgs mechanism to confer mass to particles, string theory naturally assigns mass to particles based on the energy of string oscillations. The various vibrational modes of a string correspond to particles with different masses. This interconnectedness of particles via string vibrations constitutes a fundamental aspect of string theory. String theory also suggests the existence of a minimum length scale in the universe, known as the Planck length, which measures about 1.6 x 10⁻⁻35 meters. This scale represents the smallest possible distance in our universe and plays a crucial role in addressing questions regarding singularities, such as those encountered at the cores of black holes or during the moment of the Big Bang. According to string theory, at the Planck scale, the fabric of space and time itself may exhibit a different structure than our conventional understanding. A fundamental aspect of string theory involves the unification of forces. In the standard model, there exist four fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. String theory endeavors to merge these forces within a single mathematical framework. It proposes that the diverse vibrational modes of strings correspond not only to different particles, but also to different forces, potentially elucidating all forces as diverse manifestations of a unified underlying principle. The concept of unifying forces is intimately linked to supersymmetry, a fundamental aspect of string theory. Supersymmetry proposes that for every known particle, fermion, there exists a corresponding superpartner, boson, and vice versa. Despite not yet being observed in experiments, supersymmetry plays a vital role in string theory by stabilizing the theory and potentially resolving certain issues within the standard model. However, it's important to acknowledge that string theory encounters its fair share of obstacles and controversies. One of the primary criticisms revolves around the lack of empirical evidence. Despite being an active area of research for many decades, string theory has yet to yield concrete, testable predictions that could be experimentally verified. This absence of experimental validation has led to skepticism from physicists, including Nobel laureate Roger Penrose, regarding the scientific validity of string theory. Roger Penrose, a prominent theoretical physicist and mathematician, is celebrated for his significant contributions to various fields of physics, particularly in the domains of black holes and cosmology. While his work has been groundbreaking and accolade-worthy, Penrose has also expressed reservations about string theory, raising questions about its scientific credibility. You see, a fundamental aspect of the scientific method relies on empirical evidence to either confirm or refute a theory. Penrose's skepticism towards string theory arises from its limited experimental support. Unlike well-established theories in physics, such as quantum electrodynamics or general relativity, string theory lacks testable predictions that can be verified through experiments. This lack of empirical validation raises doubts about the scientific validity of string theory. Despite being around for decades and showcasing intriguing mathematical advancements, string theory still faces a significant hurdle due to its inability to generate testable predictions that can be verified in the laboratory or through astronomical observations. Penrose's perspective emphasizes that a scientific theory should be able to make predictions and withstand empirical scrutiny. Without this ability, the classification of string theory as a scientific theory comes into question. This concern resonates with the broader scientific community's expectations regarding the falsifiability and empirical validation of theories. String theory faces criticism for its mathematical complexity. It often deals with a higher number of dimensions, typically 10 or 11, which surpasses our familiar 3 spatial dimensions and 1 time dimension. The inclusion of additional dimensions beyond our everyday experience is a key aspect of string theory, necessary to accommodate the vibrations of strings and unify forces and particles. However, the complexity of string theory poses challenges in understanding and working with the theory. Penrose has argued that its mathematical intricacy and abstract nature make it less intuitive and, from his perspective, less appealing as a fundamental theory of the universe. Throughout history, simplicity and elegance have guided the development of successful physical theories, and Penrose's stance highlights the unconventional nature of string theory in this regard. Penrose has raised doubts about the internal coherence and predictive power of string theory. While string theory seeks to achieve unity, the sheer number of possible string configurations and the various options for Calabi-Yau shapes used to compactify extra dimensions have resulted in a proliferation of potential solutions. This abundance of solutions has made it difficult to identify specific predictions for the theory, complicating its experimental verifiability. Moreover, the idea of supersymmetry, which is integral to string theory, has yet to be empirically validated. Supersymmetric particles, or superpartners, have not been detected in experiments, sparking discussions within the scientific community about the validity of supersymmetry as a fundamental aspect of the universe or merely a theoretical construct. In this light, Penrose's critique emphasizes the importance of a theory possessing internal coherence and the capacity to generate clear predictions that can be tested against empirical data. Penrose's critique expands beyond scientific realms into aesthetics and philosophy. He argues that string theory lacks the elegance and beauty typically found in successful physical theories. He emphasizes the importance of a theory's aesthetic appeal as an indicator of its potential to accurately depict the universe's true nature. Additionally, Penrose's contributions to cosmology have led him to develop alternative models, such as conformal cyclic cosmology, offering different perspectives on the universe's origin and structure. These alternatives reflect his dedication to exploring new ideas that may better align with his philosophical and aesthetic preferences. Now, let's explore why Sir Roger Penrose, a distinguished physicist and mathematician, questions the existence of dark matter despite its widespread acceptance in the scientific community. Penrose's skepticism regarding dark matter stems from his inclination towards an alternative explanation for the gravitational anomalies observed in galaxies and galactic clusters. Instead of proposing the existence of unseen and undiscovered dark matter, Penrose presents a different viewpoint on understanding these peculiarities. His alternative theory, known as conformal cyclic cosmology, CCC, posits that the gravitational effects attributed to dark matter could actually result from the universe's inherent structure and the expansion of space itself. Within the CCC framework, Penrose challenges the concept of dark matter by suggesting that the universe's expansion leads to the gradual conversion of massive particles into massless particles over immensely long periods. According to Penrose, this conversion could contribute to the gravitational effects often associated with dark matter. Essentially, he contends that dark matter may not be necessary, as these effects could be elucidated by the behavior of particles as they lose mass over time. Penrose's unconventional standpoint on dark matter reflects his preference for simple and elegant scientific theories. He argues that his CCC model offers a more straightforward and aesthetically pleasing explanation for phenomena commonly attributed to dark matter, aligning with his broader philosophical and aesthetic sensibilities. What do you think about Roger Penrose's concepts? Are you in agreement with the notion that dark matter is non-existent? Share your thoughts in the comments below.